Okay, welcome to another live for the assumptions of physics research. I'll wait a couple of minutes to see if anybody else joins. Today, the plan is to start looking at this theory of ensemble spaces that we're putting together, which is going to essentially try to be a first level axiomatic theory for states and processes so that all our physical theories can be found within this space of theory. So what we're going to do is essentially go through the text. And I realize that some people are going to see this as a recording. And so if you guys have questions, put them in the comment, and then I'm going to try to answer them and talk about them next time. And yeah, that's how it's going to be. Forgot to get the water, so I might have to do a break for that later. So let me start getting set up here to see how this is going to work. Okay, so this is going to be this. There you go. And as usual, I have to make the chat. This one, no. Did they change the interface? There you go. So I can move this on the other side. And this can be a little bit wider, I think. Okay. Okay, ready. So in this chapter, we aim to develop a general theory of states and processes that is applicable to any physical system. The core concept is that of an ensemble, and the goal is to find the necessary requirements for ensembles that can serve as basic axioms and then further suitable assumptions to recover the different theories, such as classical, quantum, or thermodynamics. This kind of, we're going to be doing some type of inverse statistical mechanics, in the sense that in statistical mechanics, you first assume that there are like your perfectly defined states or the states as they are in the theory, like in classical mechanics would be points in phase space. In quantum mechanics, they would be your arrays in a Hilbert space, and in classical field theories, right? The state would be the full definition of all the field configuration. And then you create statistics on top. So here we're going to do exactly the opposite. We are basically going to say we have a theory that has ensembles, and ensembles have always the same property in any physical theory. There are some things that ensembles always need to do. And then we're going to find the different statistical theory, classical mechanics, quantum mechanics, as basically those ensemble spaces in which the states that become further and further defined, the ensembles that are further and further defined, have some special properties. And that allows us to generalize a lot of results that we would have both in classical mechanics, in quantum mechanics, and field theory, and put them at sort of at a more general level. And that's kind of the idea. The idea is that just the fact that you have ensembles already constrains the theory a lot. So the basic premise is that physical theories are primarily about ensembles. At a practical level, most of the time, we can only prepare and measure statistical properties as we do not have perfect control over any system. That is, all measurements are really statistical. And people sometimes do this in sort of generalized probability theories or even in introduction of quantum mechanics, that they concentrate on the measures on themselves. And what we're doing here is also concentrating on the preparations. The cases where properties can be prepared with 100% reliability can still be understood as ensemble of identical preparation. At a conceptual level, the goal of physics is to write laws that apply all the time. Every time that one prepares a system according to a particular procedure and lets it evolve in particular conditions, he will obtain a particular result. That is, the idea of repeatability of experimental results implicitly assume that the objects of scientific inquiry are not single instances, but the infinite collection of all reproducible instances. This means that any physical theory, at the very least, will have to provide a mathematical representation for its ensembles. So it might give you more, but at least it needs to give you the description of ensembles and ensembles, how do they work. And so this is sort of let's say a philosophical justification for the work. And if somebody is a philosopher, perhaps can take this and expand it and make it a lot more streamlined. But for me, this is fine. By ensemble, we mean what is usually meant in statistical mechanics. We have a preparation device that follows some known recipe. Its output is varied, but is consistently varied. That is, its statistical properties are well defined. The collection of all possible outputs taken as one object is an ensemble. In classical physics, ensembles are probability distribution over the full description of the system over phase space for classical mechanics. In quantum mechanics, ensembles are represented by density matrices and density operators. In the standard approach, statistical ensembles are defined on top of the space of true physical space, so microstates and pure states in quantum mechanics. We will proceed in the opposite way. We will start from the ensembles and recover the space of the most pure ensembles. And these are going to be the microstate in classical mechanics and the pure state in quantum mechanics. There are two main advantages. The first is that we can create a theory that is agnostic about what the fundamental states are and is therefore general. The second is that this approach is more in line with experimental practice. The experimental data is about statistical ensembles only, and the pure states are idealizations that are useful as a mental model or for calculation. There are three main requirements for ensemble. First, they must be experimentally well-defined. This means that there need to be enough experimentally verifiable statements and experimental tests to fully characterize them, and this will impose a topology on the ensemble space. And this is what we looked at last time, that we already have a theory that is well-developed that links experimental verifiability to the notion of a topology, such that the topology in physics is actually there to characterize experimental verifiability. Second, we can always perform a statistical mixture. Given two ensembles, we can create a third by selecting the first or the second according to a certain probability. This will impose a convex structure on the ensemble space. So I can always prepare a sample at a particular energy level or a particular temperature or whatever we want to, or one procedure can be. And we have another one with a different level of energy or temperature and so on. And then I can simply select between the two. I take one 30% of the time, the other one 70% of the time. If I box all this together, this is going to be a new preparation, and therefore it's going to correspond to a new ensemble. And so the idea is that this ability to do this statistical mixture gives us this convex structure. And a convex structure, it's like a linear structure. You're making linear combinations, but the coefficients have to sum to 1, and they all cannot be negative, right? So a linear combination, you can sum any, the coefficient of the linear combination can be any, if we are reals, any real number. So it can be -2 and +5. If it's an affine combination, then it has to sum to 1. So you could have -1 and +2, and this would still sum to 1 instead of fine combination. And a convex combination, instead, it's 1 for which you can only have non-negative numbers. So 0.3 and 0.7, that would be good. And the idea, the insight is that this convex structure that comes from the statistical mixing is the one that is responsible for all linear structures in physics. So all the vector spaces that you might have in terms of probability distribution on function spaces, in phase space, in quantum mechanics, at the end of the day, they all come from this assumption that ensembles have to be able to have a convex structure, that you must be able to mix them. And third, ensembles will need a well-defined entropy which quantifies the variability of the elements within the ensemble, right? So the ensembles are going to be in some sense in an equilibrium because they have to have the statistical properties must be well defined, and one of the statistical property is the ensemble. And we already had done some work that showed that if you have an ensemble in equilibrium, then the variability of the elements in the ensembles, how different they are from each other, actually is it is the Shannon entropy. The Shannon entropy is the only indicator of variability of elements within a set that is monotonic, continuous, and linear in probability. And all those things are things that we're going to see later while we develop the theory. This is just an overview of how the whole thing needs to work. Since the variability cannot decrease when performing the statistical mixture and can only increase up to the variability introduced by the selection, the entropy will have to satisfy certain bounds. And these bounds actually, and this property of the entropy is essentially what gives the geometric, gives us all the geometric structure that we have in physics. So the symplectic nature, the symplectic structure in phase space, the volumes that we have in phase space, that all comes from entropy. The inner product that you have in quantum mechanics, that also can be shown to be coming from entropy. The information theoretic geometry that one does also, of course, that's tied to entropy, and also the geometry of space-time. So that comes from entropy. So the idea is really to, from these three assumptions, from these three assumptions on ensembles, see how all these other structures come and they develop. So from these axioms, many general results can be proven. An ensemble space will be a convex subset of a vector space that will extend over a bounded interval in each direction. The concavity of the entropy will impose a metric over the space, turning it into a geometric space and a metrizable topological space. Each ensemble can be characterized by a subadditive measure, which becomes a probability measure in the classical case. And this makes the physical theory a lot more constrained than one might imagine at first. So that's basically the goal of these things. Why we're doing this? To show that physical theories have to follow a pattern that is very strict, because physical theory at least have to be able to talk about ensembles, and ensembles have to have particular properties. And so this is one note that I still don't know where to put, the fact that all the logs are going to be assumed in base 2. So what we are going to do for today, because I don't think there's going to be time for much else, we are going to review essentially how ensembles work in both classical mechanics, discrete and continuous, and in quantum mechanics. And we're going to see that there are some issues and some problems with essentially the infinite dimensional cases, both in classical mechanics and quantum mechanics. And these are the things that if we want to get the axioms right and everything working right, we need to understand what those issues are and what the problems are. So part of doing this exercise is to make sure that the text as written makes sense. So if you guys have comments and questions, or if you see problems, please put them in a chat. Or you can, if you're watching this later, you can write a comment on YouTube and I'll try to address it next time, or you can even just write me an email. But this is why I'm trying to do this, because I want to have as many eyeball on these things to make sure that it's reasonably well explained, and all the connections between all these different ideas and fields actually make sense. Okay, so let's start by reviewing the standard cases. We'll start this chapter by reviewing three cases: discrete classical ensembles, continuous classical ensembles, and quantum ensembles. These will be useful both to form an intuition for ensembles and to serve as targets that the whole theory needs to reproduce. We will also go through a series of problematic details and exceptions that we will need to address in the development of the general theory. So discrete classical ensemble space. A discrete classical ensemble space is the space of probability distribution over a countable number of cases. This is a typical thing. You have a coin, it can be head or tails, or you have all the things that are related to gambling. You have the dice, you have the roulette, or you have anyway cases that are distinct from one another, that do not form a continuum. And mathematically, that is, a discrete classical space is a simplex containing n points, possibly countably infinite, that for each and for which every element in the simplex in E is characterized by a unique convex combination, E equals the sum over pi times Si, such that all the pi's sum to 1. And now that I noticed this, I didn't specify that the pi have to be greater than 0, or greater or less or equal to 0. So this is exactly why we do this, to note these things, such that the pi and pi greater than equal to 0. And I forgot the 0. There you go. Okay, so I probably forgot that many, many times around, but this is the difference between an affine combination and a convex combination, and a probability mixture is a convex combination. The space is closed under convex combination of finitely many elements. So if you take, if you have two probability distributions, you can say, I'm going to take 30% of this probability distribution and 70% of this probability distribution. You sum them, you have another probability distribution. So not only you can make a probability distribution over the points, but you can also make a statistical mixture of probability distributions. And the entropy is given by minus the sum of pi log pi. This is in the classical, discrete classical case, so that's what you have. So in the final case, the space of classical distribution over a discrete space corresponds to a simplex. And the simplex is essentially a geometrical shape that kind of works like this. If you have one element, you just have a point. If you have two elements, you have the segment between the 2 points. If you have 3 elements, then you have the triangle. And you note that each side of the triangle is a line, which is the simplex or order 2. And then if you make a 3-dimensional simplex, when you have 4 points, you essentially have the triangular pyramid. And again, the triangular pyramid, each side is a triangle, and each side of the triangle is a segment, and so on. And so if you have if you have 5 points, you have a 4-dimensional geometrical object that sort of generalizes this pattern, right? It's going to be something that lives in 4 dimensions, but each side is a 3-dimensional triangular pyramid, and so on. This is just a link to Wikipedia, by the way. In the final case, the pure states are finitely many, and each ensemble is uniquely identified by the composition of pure states. So each ensemble is a probability distribution over the points. Effectively, each ensemble is a probability distribution over the pure states. Mathematically, each point of the space is a convex combination of the vertices, and the simplex has a central point which corresponds to the maximally mixed state, a uniform distribution over all pure states. And this is where you can start understanding convex combination as a sort of a geometrical element. So if you have, if I said before that the simplex of 2 elements is a segment. And so on one side of the segment, let's say you have 100% in point A, so 100% heads. On the other extreme of the segment, you have 100% tails, and in the middle, you have all the possible probability distributions, and the one in the middle corresponds to the uniform distribution of 50% heads and 50% tails. And the closer you are to tails, the more the probability is going to be greater than 1. And so when you have 2 points, the convex combinations are essentially all the points that are in between, the segment in between. The affine combination, if you have 2 points, it's the line that goes through them. And instead, the linear combination is the plane that goes from 0 and connects those 2 points. So that's how the geometry works. And again, whatever simplest that you have, if you have a triangle, the middle point of the triangle, the barycenter, is going to be the uniform distribution. It's going to represent the uniform distribution of that probability space. So the entropy is given by the Shannon entropy, which is minus pi log pi. This means that the entropy of each pure state is 0, because if you put 1 and 0 and 0, you're going to have a 0. And the entropy of the maximally mixed state is log n, where n is the number of pure states. So if you put the pi, you put a 1 over n here, the minus the logarithm of 1 over n becomes n, and then you just have the sum of 1 over n times, so that's going to sum to 1, so you're going to get log n. The entropy increases as we go from pure states to the maximally mixed states, and the level sets of the entropy form a series of concentric shells. So if you imagine that you have the triangle, right? The vertices of a triangle are pure state. They have 0 entropy. The middle of the triangle is going to have log 3. And then you can imagine that as you go inside, the entropy keeps increasing. So you're going to have level sets of equal entropy. And these, as the entropy increases, they become more and more closer to the center. Note that imposing 0 entropy on all pure states is a restricted condition that does not apply in general. To see this, consider the case where the state is defined by the number of molecules of 2 substances. This space is the product of 2 independent variables, NA and NB. If we have a uniform distribution over NA cases of NA and NB cases of NB, the total number of cases is the product of the 2, right? So you imagine that you have on one dimension, you have NA, the other dimension of NB, you get a square or a rectangle, and the rectangle is essentially the number of cases that you can have. Therefore, the entropy of the joint state is the sum of the entropy of the marginals. This because the distributions are independent. However, if we pair Na with the total number of molecules, then we have a problem, because the issue is that the variable Na plus b corresponds to a variable number of joint cases. Therefore, the case where the ensemble space is a simplex, but the entropy is not the Shannon entropy, is the Shannon entropy plus the contribution of the entropy for each vertex, is a physically meaningful case that should be possible in the general theory. So the whole point of this is that here we are assuming that the entropy is this function, and this function only is good if you're assuming that essentially all the states, all the pure states give you the same amount of information. Like they're describable by the same number of bits, the same number of precision, whatever you want to call it, right? They're essentially homogeneous in that sense. And you might have cases where that's not the case. So that's one case. When we're developing the general theory, we have to be cognizant. We have to know whether that's a problem. Okay. Again, if there are questions about this, put in the chat, put it down in the comment. It's why we're doing this. And so we're seeing the finite case. Now we are going to look at the countable case. The countable case, you can imagine that you don't have 5 elements, 6 elements, but you have infinitely many. So again, if we have number of particles, there is no maximum number of particles. In principle, we could have a distribution over arbitrarily many particles. It's not really infinite because we're not going to have infinitely many number of particles. Each case is finite, but there is no maximum. That's basically what the countable case is for. So the opposite extension is to include all sequences, all the pi, whose sum converges to 1. And this would be the space of all probability measure over a countable discrete space. And since we cannot create a uniform distribution over infinitely many cases, there is no center point. There is no barycenter. There is no uniform distribution over infinitely many. And so effectively, there is a hole in the middle, right? So if we imagine that the triangle, we had the point in the middle. Now, when we're having this infinite many points, we don't have a barycenter. We don't have a middle point. And this is something that I personally still don't understand exactly how this works. And in fact, I have a footnote here that it may be useful to characterize this hole and the limit points. There should be at least one limit points for each sequence pi whose sum converges to a finite probability that it's less than one. Because the idea is that you can take a probability distribution on finitely many elements, and then you can take the rest. So let's say that that distribution over 5 elements sums to 80%. And now you can take that remaining 20% and try to spread it as uniformly as possible on the remaining one, right? So that would kind of make, again, one of these limit distributions that are not in the space, but you can you can approximate as close as you want, and that's going to be a different limit that you can create. So there should be a limit for each type of this. So intuitively, we can clip the part of distribution constant, while we spread the rest uniformly to other cases. Each should reach a different limit point. So I have no idea what the space of this is. Maybe it's useful to characterize, maybe not. I have no idea. That's the extent of my knowledge stops there. However, there is a problem. Even if we did this, there is another problem. The space of all probability measures is too large. Note that the entropy is not finite for all coefficients that sum to one. So for over infinite convex combination. For details, see this article, and this is an article that I found on the archive that basically shows that there are some probability distribution for which the entropy diverges. It's not well defined. It's infinite, whatever you want to call it. But you do not have a finite entropy. And since we said that ensemble must have an entropy well defined, these cases must be ruled out. They are going to be unphysical. Given that we want the entropy to exist and be finite for all ensembles, this generalization, like the one provided here, does not seem physically warranted. And this is something it's a reference that I sometimes use, the NCAT lab, and they talk about super convex spaces where you can do the infinite combinations because they want to generalize some things. That's not going to be the right space for us. It's not clear to me what is the right space. And that's kind of part of the problem, but it's definitely not spaceable probability measure. That's too big. Also note that expectation values are not guaranteed to be finite either, and requiring a particular observer to be finite further restricts the space. This restriction may be desirable for another reason. A discrete ensemble space has no notion of ordering of the pure states. So you can take a set of points and you can make an infinite permutation, and you would still have a set of coefficients that sum to one. And again, this would be a problem if we imagine that you have that the entropy is not well defined for all essentially for all sequences that converge, because you might take something where the entropy is well defined and then reorder it, and now you have something that that has an entropy that is not well defined. So there is something in the ordering that actually it seems to be important. Okay, so this restriction may be desirable for another reason. A discrete ensemble space has no notion of ordering other pure states. Physically, this would mean that the states with 1, 100, or 1 trillion particles are equally distant. So all infinite permutation are allowed, requiring the expectation of the number of particles to be finite, which is the sum of ni, so basically of I, multiplied by pi is less than infinity, should effectively encode the infinite ordering in the rate of the convergence of probability distribution, so that not all infinite permutation would be allowed. And this kind of makes sense because whenever we have infinity in physics, as we said before, it's not really that we are infinite, it's that at some point we stop. There is some large number, we just don't know what that largest number is, and so we include all the potentially higher numbers, but there is no there's nothing really infinite that is going on. It's everything is finite, but we don't know where we are in this finite scale. And so imposing some type of well, we have to go, the probability has to go down at a certain speed such that some expectation value of something has to be well defined. Then basically it's putting let's say a bound in some sense to how things can go to infinity. It's giving us more of a sense of what that infinity is. And again, all of these things are still not clear to me. These are problems that I uncovered when looking more closely at quantum mechanics, because quantum mechanics is like natively more of a statistical theory, and so you see this problem more come to the light. But it's a problem that we also have as we saw in discrete classical probability, and this needs to be addressed in some way. And I still don't know exactly what is the correct way to address these infinities, but they're there. And having done the accountable case, then we can show that there can't be an uncountable case. The uncountable infinite case is not physically relevant. There is no second countable discrete topologies. Cases are not experimentally decidable. You can't basically explore a space like that experimentally. And then there is also a mathematical problem. Also note that any set of real numbers whose sum is finite can only can have only countably many non-zero elements, right? So if you say I have a set of numbers, they sum to one, they can't be more than countably many. And to understand why, note that there can only be finitely many terms about any particular positive value if their sum is to remain finite. So if I have a bunch of points and I assign a probability to each of them, and the probability is finite, right? Only finitely many can have a finite probability. And so if I extend this to infinity, then I can only have countably many. I'm never going to be able to reach uncountably many. So effectively, the uncountable case would be stitching together infinite many cases. And this is kind of what happens or what people try to do when they try to study non-separable Hilbert spaces for quantum mechanics, because non-separable Hilbert spaces, they would have a base that is uncountable. But then it means that whenever you're trying to make a superposition, you can make only a superposition of finitely many elements, precisely because of this, because you can only spread something finite over countably many elements. And so effectively you have this like a space where there are all these infinitely many countable subset that then they can't really talk to each other. So it's basically physical garbage. So it doesn't really work. Okay, so that was the countable case. So there was the discrete case. And now we can have a look at the continuous case. Continuous classical ensemble space is the space of probability distribution over phase space. And by phase space, I mean the usual position and momentum space. Except that in classical mechanics, you also have another space of states, which is typically the sphere, the surface of a two-dimensional sphere, because that's where you do what's it called, angular momentum type thing. So that also is a valid space, and I'll call it just phase space because. And so there is the space of probability measure of our symplectic manifold that is absolutely continuous with respect to the Liouville measure, right? So this symplectic manifold is basically this idea that you have conjugate quantities and you can assign areas to these conjugate quantities to count the configuration. It's just a mathematical term. And again, the two-dimensional sphere would also qualify as symplectic manifold. So in the mathematical definition, we are looking at that. And then we have, again, each ensemble is a probability measure, probability distribution over these measure that is absolutely continuous with respect to the Liouville measure. This means that you can't assign finite probability to a measure zero set in phase space. So if you have a set of measure zero in phase space. It could be, for example, a single point. A single point has no volume, so it's a measure zero space, a measure zero set, and you can't assign a finite probability on a single point. If you did, you wouldn't have a probability distribution. The probability distribution would be infinite because it would be a probability density. And so the fact that you have the measure that it's absolutely continuous with respect to the Liouville measure, it means that you can define a probability distribution. And the probability distribution, because the probability distribution, the probability density is important because the entropy is given by the Shannon-Gibbs entropy calculated using the probability distribution, the probability density. And the Radon-Nikodym, the probability density mathematically is the Radon-Nikodym derivative between the probability measure and the Liouville measure, the count of states. And these things exist only if you have this idea that for each set that has zero state, you can't assign finite probability, which again, physically makes total sense. And the expression for the entropy is minus the integral over the whole space of rho log rho. And the rho log rho is this derivative, and this mu is the Liouville measure. You know what? I should, no, I have it here, the Liouville measure mu. So P is the measure, the probability, and mu is the Liouville measure. Okay, so that's basically what we have. In a very simple term, we have these density distributions over phase space that are always greater than zero, and the sum to one. Those are the probability density as we expected. In the continuous case, the space of ensembles is a space of integral function over a symplectic manifold over phase space that integrate to one. That is, if X is the symplectic manifold, then the set of ensembles is the space of spaces that are integral, and they integrate to one on this Liouville measure, on that particular thing, where mu of u is the integral of the symplectic form times n. It's Liouville measure. It's the thing that counts the states in our phase space. There are no extreme points in the convex space, meaning that there are no ensembles that cannot be written as a convex combination of other ensembles. So in the discrete case, you have, let's say, a triangle, right? That point of the triangle, the vertices of the triangle, cannot be written as a convex combination because you don't have 2 points around them, and that point is the vertices are not between 2 points. And that's why they can't be written in a convex combination. The discrete space have this feature that they have extreme points. If we have distributions instead over a continuum, wherever you take a distribution, however tight it is, you can always find some other smaller distribution contained inside. And so you can always say that this distribution is the sum with this distribution, plus the rest. And so there are no extreme points. Ideally, well, let's read because probably I say so. There are no extreme points in the convex combination, meaning there are no ensembles that cannot be written as a convex combination of other ensembles. This is important as when developing standard constructions in the ensemble space, one cannot rely on the existence of extreme points. So this idea that everything is some distribution on perfect cases, that doesn't work even in classical continuum. The delta distributions are not part of the space, so you can't, so the sort of the points having a 100 distribution of 1 point, it's that probability measure is not in the space. In fact, the relative measures are not absolutely the relative measure, the discrete measure, the discrete measures are not absolutely continuous with respect to the Liouville measure. They assign non-zero probability of a set of measures zero. Therefore, one should not think of delta distribution as pure states. It doesn't work. There is a difference between the spectra, so the space of possible value of a random variable, so the space of outcome of position and momentum, and the states, the distribution, which will be even more pronounced in quantum case. And I write this because I had that intuition that, a probability distribution is just the convex combination of the possible outcomes on the continuum. It just doesn't work. Like you cannot generalize that that way of thinking, either mathematically or conceptually. You have to throw it out and look for other things, and the other things are actually more. They're better for classical mechanics, and they're also better for quantum mechanics. It's one of those things where you get things that actually uh, make more sense. So you cannot have one of the reasons why you can't have the discrete measure. This would have infinite minus infinite entropy. Like the entropy would be minus infinity. It doesn't work. So those things are just not there. The symplectic nature of the manifold is required to assign a frame invariant density to states and a frame invariant notions of independence of degrees of freedom, as we saw in the classical mechanics section of reverse physics. This is something that I know that it needs to happen more in general in the space of ensembles, but I still don't know what is the correct mathematical specification, but we keep in the back of our mind that because this is something that needs to happen. And then the entropy is given by minus the integral of rho log rho, where mu is the Liouville measure and rho is the probability density over canonical coordinate. And it's important that this rho is defined in terms of position momentum, because if a different measure is used or if the coordinates are not canonical, the formula gives the wrong result. So those are important. Similarly, to the countable discrete case, the entropy can be infinite and the expectation values can be infinite. And the other complication is the frame invariance. It would not make sense to have the expectation for position in one frame to be finite while infinite in another. Requiring all functions of position or momentum to have finite expectation restricts the distribution to those with finite support. And requiring that all polynomial functions of position or momentums have a finite expectation restricts the distribution to those that decay faster than any polynomial. Again, I don't know exactly what is the correct space of distribution. The idea is that anything that integrates to one might be problematic because it might not have an entropy that is well defined, and it might have this issue that the expectation for position is infinite, or the average energy is infinite. All those things do not make physical sense. And so if you say, okay, I have a position and momentum, and I want any expectation of any function of these to have finite. So position is finite, then any polynomial of position has to be finite. You know, x to the n has to be finite. The exponential of x has to be finite. The exponential of the position has to be finite. So if you require any function of position to be finite, then the functions that are left are the ones that are finite support, the ones that don't extend to the infinity. Because however slow they go to infinity, you're going to have to find a function that diverges faster than that, and then the expectation value is not going to be finite. Now, there is a sense that these types of transformation might also be too big, and it might be that the polynomials are actually the things that sort of make sense, because if you have if you imagine to have a transformation in which the average position depend on the other a position of the time step before, for example, by x square. If you compose this enough time in particular ways, you're gonna be able to get all the polynomials. And so either like all transformations are linear, and then you stay in the linear domain, or as soon as you have a mild nonlinearity, you get all the polynomials. But you can stay in the polynomials, and then sort of there is a class of functions again, past that. All those things are things that I've seen intuitively. I haven't actually, I don't have a consistent theory of how these classes work, and if they are well defined and so on. And so I haven't really figured out what is this problem yet. I just know that there is a problem, and I don't know how to address it, but here it is. So there is a question. Cram, I completely overlooked the time. Could totally have been here half an hour ago. Oops. depending whether I should backtrack or just jump in. I would say stay on time right now, and if you are completely not understanding what I'm saying, go back. But you might be fine. Okay, so we still have this problem that space of distribution, continuous distribution in phase space is going to be too big. I don't know what is the right class of distributions. And so for now, all the things that I'm trying to prove, they try to avoid this problem. And there is actually a way to do it. So for now, I'm fine. Okay, so unlike the discrete classical case, subspaces and dimensionality of subspaces cannot be defined without an entropy. The issue is that we need a measure on the set of pure states, and the convex structure cannot provide it. So this is where other work that I've seen in generalizing probability in some sense does not work because these other work only imagine that there is this convex structure that you can take probability and put them together and make a linear combination. And the issue is that if you want to be able to know how many cases you have, right? If you have these extreme points, and then you can go and count them, everything is fine, and you have a discrete space. But if you don't have these extreme points, because as we said before, a probability distribution over continuum can only be seen as the mixture other two probability distribution that can also be seen as a mixture of probability distribution and so on. You don't really have a way to count the number of cases, and so the only thing that you can say is that they're infinite. But then, since you have these subspaces that you say they are all infinite, you can't compare them to one another. You can't say this is double than the other and so on. And there you go. That you can't understand the dimensionality of this space. So the issue is that we need a measure on the set of pure states, and the convex structure cannot provide it because you're not going to be able to have this. You're not going to be able to find extreme points and count them. And the entropy, however, does. He's able to count how many states you have, because the supremum of the entropy for all distribution with a specific support u is the logarithm of the measure of u, right? So in the same way that in classical statistical mechanics, right, you basically can say if you have a uniform distribution of a region, then the entropy is the logarithm of the number of states in that region. You can kind of do the opposite. If I have an entropy well defined and I say, oh, I know that I have a region of phase space. I look for all the possible distribution there. I take the one that has the highest entropy. Well, the one of the highest entropy is the uniform distribution. And now you know how much the entropy of the uniform distribution is. And then you take the exponential of that, and now you know the number of states that are in that region. And so you can use the entropy in this way to recover the size of things. As we'll see, the entropy can be used to both identify substates and recover the Liouville measure. A lot of it that we do in the ensemble space is actually to use the entropy to rederive a bunch of things, including subspacing and Liouville measure and analog things for quantum mechanics. So going forward, it is a bit unclear whether discontinuous distribution should be included or not. I am starting to have a better idea, actually, as of yesterday, because I finally solved yesterday a big confusion that I had in my head. Originally, we thought that probability density should be continuous, as only continuous functions can physically represent experimental relation. This is from the previous work. However, the relation given by the measure is not between points and probability, but rather between sets and probability. This is the most important thing in a probability theory that most physicists don't get because they haven't studied measure theory. In the discrete space, it's always okay to think that you're assigning the probability to the points, But on a continuum, you can't assign probability to the points because the points have measure zero. So you can't build the probability like that. What you do is assign probability to sets. I have a region of phase space, right? How much probability is assigned to that region of phase space? And again, because measurement, when you are on a continuum, are only on finite ranges. So you're essentially asking, what is the probability to find the particle in this region? What is the probability that my state is in this region? And that always makes sense. And so that's essentially how you should think of probability. Probability is not something that takes a point and gives you a probability, but probability is on regions. So probability density is, in a sense, not the prime physical object. The measure is. The probability density, in fact, is not even uniquely defined, as countably many discontinuities can be added, and the measure is not changed. This is also something that it's true in quantum mechanics. People think the state of quantum mechanics being the wave function. Well, it's not really the wave function. It's the equivalence class of wave function that look the same under the inner product, because the inner product does an integration. And when you're doing the integration, all the values on a set of measure zero are completely relevant. So again, imagine that you have a uniform distribution between 0 and 1, right? And so the probability is always 1, except at a point where at point the probability density is 2. When you integrate, the fact that you have that discontinuity doesn't really matter. Even if you assign 2 for all the rational numbers, which are infinitely many, those 2's don't count because that's a set of measure 0. So the point is that the probability density is not even defined uniquely, is defined essentially up to all these things that you can in principle put and would be irrelevant. And so that's what's convincing me more and more that we can have this continuous function is not a problem, because the physical relationship, the experimental relationship is not between points. And then yesterday I figured out that in the construction that I was doing, there was a property that I thought was there, instead was not, and that property made me a little bit confused. And now that it's not there, I know that things are going to work out well and so on. So I do think that we are going to have, we're going to allow for distribution that have a probability density that is discontinuous. Is not going to be a problem, which is nice, because then if we are on a finite range, we can get the uniform distribution, and the uniform distribution is there and is the one that maximizes the entropy over that interval. So even mathematically, we get some convenience. Okay, so there is a question here. This is also why taking discrete Shannon entropy and making the sum an integral is also false, right? Yeah, so that we saw before. If you're on a continuum, the entropy is defined by the probability density. And the probability density has to be taken according to the correct measure. And that measure is the count of states. So you're really looking at probability per state, and then you're calculating the Shannon entropy on that. And that this has to be done, this density exists only if the measure is absolutely continuous. So if you're not assigning finite probability to sets that have zero states, where the Lewis measure is zero. And the fact that the units must be right, this is a note that I have here. Rho is a probability density over canonical coordinates. If a different measure is used, is not used the Lewis-Mills measure, or the coordinates are not canonical, then you get the wrong result for the entropy. So you must use these things. Okay, so that's basically the review for classical mechanics, and as I imagine, this already took an hour. And so now we're going to review the quantum case, and then probably call it a day, and then probably figure out whether we want to do next week or not. Probably not, because it's break, and we probably continue after that. Okay, so now for quantum mechanics. A quantum ensemble space is the space given by the density matrices or densities operator of a Hilbert space equipped with the von Neumann entropy. Okay, so in quantum mechanics, the distribution, the statistical mixed state are given by density matrices or density operators, and the von Neumann entropy is how you calculate the entropy of the mixed state. So that is given a separable Hilbert space H representing a quantum system. The ensemble space is a space of positive semi-definite self-adjoint operators with trans 1, M of H, and the space of pure state is given by the projective space P of H, and the entropy of the ensemble rho, which is in the space of positive semi-definite self-adjoint operator with trace 1, is given by the von Neumann entropy, which is minus the trace of rho log rho. Okay, these are all standard definitions. So again, like in the discrete case, we're going to look at the finite dimensional case, which is absolutely clear. And then we'll talk a little bit about the infinite dimensional case, which has all the problems that we already discussed for classical mechanics. And we'll also have additional problems, because why not? The simplest non-trivial case is the qubit, which is the block ball, for which the block ball is the space of ensembles MH. So again, you have a ball, and the interior of the block ball corresponds to the mixtures, while the surface corresponds to the pure state. And the pure state you can always write in such manner with this cat-Brown notation. In quantum ensemble spaces, there is no unique decomposition in terms of pure states. Note that the space is exactly characterized by knowing which different mixtures provide the same ensemble. So in classical discrete, we saw that every point has one unique decomposition in terms of the extreme points. So if I have a segment, then I have these two extreme points. Each point is exactly one linear combination of the two. If you have the triangle, each point in the interior is exactly a convex combination of the three extreme points. And the way that you can imagine this convex combination when you have more than two, imagine that this triangle is embedded in a Euclidean plane, and each point, extreme point, is actually the vector that goes from 0 to that, and you make a convex combination, linear combination that are always non-negative and they sum to 1, and you get the point that you're going to get. So it's just that. There's nothing weird going on. Now, if you have a sphere, right, and all the extreme points are the points on the surface of the sphere, because again, you can't express any of those as a linear combination of anything else, because if you take a line, half of the line at least will always gonna be outside, so you can't take 2 points and obtain obtain a segment with 1 point inside that it's also on the surface. And so those are all your extreme points. None of those can be seen as a convex combination. And now you take a point in the middle, like the center point, for example. The center point can be expressed as a linear combination, as a convex combination of any two extreme points. And so you don't have a single probability distribution. You have multiple probability distribution. And that's why quantum mechanics is different from classical mechanics. You have this multiple decomposition. The multiple decomposition makes the ensemble space behave in a way that is a hybrid between the classical discrete space and continuous. Pure states are properly a part of the ensemble space, as in the discrete case, and we describe each mixture in terms of finitely many pure states. However, the pure states form a continuum. Therefore, we can also define probability density over the space. We can define the context integral. For example, for a single qubit, the maximally mixed state, the center of the ball, can be equally described as the equal mixture of two opposite states, say spin up and spin down, or spin left and spin right. However, it can also be described as equal mixture of the whole space. So if you have a uniform distribution over all the points on the sphere, so you basically have complete uncertainty on which pure state has been prepared, you're going to have the maximally mixed state. And so this is where classical mechanics is a hybrid between the classical and the continuum case. It can sort of kind of lives in both worlds. Note that the complex projective space are symplectic, which is what allows one to define frame invariant density. The goal is to have one argument applied to the generic definition as to why the pure states, the space of pure states must be symplectic. Also note that two-dimensional sphere is the only symplectic sphere. By homogeneity, we should be able to argue that the space is symmetric around the maximal limit state and is therefore a sphere. The symplectic requirement would select the dimension 2. Note that the real and quadratic spaces would be excluded by this argument. So this is what I was saying before. I believe that there is the requirement of invariance of entropy under the choice of units of your coordinates is going to impose in some way this symplectic structure or relatively similar a Poisson structure, something that basically tells you that you have conjugate variables and stuff like that. I still don't know how to impose it. I know that it has to be there. And if you have it there, then it's going to be able to pick out the quantum mechanics very easily, because the two-dimensional sphere or the three-dimensional ball is the only space that is symplectic. It's where you can define this form that gives you areas, in a way that does make sense. If you take like a circle, you can't do it. If you take a sphere that is n-dimensional, also you can't do it. So once you say I have a sphere and it's symplectic, it's going to be the two-dimensional sphere. It's the similar argument can be done to recover three-dimensional space. If you say that the space of directions is again symplectic, because you must be able to put the coordinate invariant distribution on all that, then you're going to say, okay, well, the two-dimensional sphere is the only symplectic sphere. Therefore, three-dimensional space is really the only thing that you can have. So there is an argument there that needs to be that is going to work. I still don't know exactly what it is, and so this is where I'm just putting it as a placeholder so that I remember that I have to do it. Okay. Then the last thing is the von Neumann entropy for the maximal limit state is a logarithm of n, like we had, for example, in a classical discrete and continuum, where n is the dimensionality of the Hilbert space. And again, we see that the maximum entropy gives us a measure of size of the space. This time, it doesn't give us a size of sets. It gives us a size of the dimensionality of the space, but it's basically very similar. Note that to calculate the von Neumann entropy, we are diagonalizing the density matrix. This means that finding a set of orthogonal pure states such that rho is the convex combination of those pure states is a convex combination. Note that the convex hull of a set of n orthogonal pure states is an n-dimensional simplex whose center is the maximum mixed state. So, for example, if you have a sphere, you have two orthogonal states. These are going to be two opposite states. And you take the convex combination of the two is going to be a segment. And a segment, as we saw before, is the simplest simplex that you can have. And this segment is going to go through the middle of the sphere, right? And therefore it contains the maximally mixed state. So this set now is exactly a classical probability state, because it has the extreme points, it has a simplex, and the entropy of the von Neumann entropy will actually coincide with the entropy of the discrete Shannon entropy that we saw before. So therefore, we are looking for a simplex that contains rho and the maximally mixed state. Whenever you are diagonalizing something, that's essentially what you're doing. In the two-dimensional case, rho is the interior of the point and the block ball, right? So if you wanted to diagonalize, this is essentially what you're doing. You have the block ball, you have a rho, which is your distribution. You take the maximally mixed state, you take the line that connects the two, and now you have a segment that has opposite points at the opposite pure states, those are going to be orthogonal, and you have basically made your orthogonal decomposition. You found eigenstates and eigenvalues. So the distance from the points will be proportional to the probability. And because of this property, the von Neumann entropy is the smallest Shannon entropy between all possible decompositions. So if you can imagine that each point in the ball can be seen as a convex combination of multiple ways that if you take a point, you can make multiple segments and multiple lines, go through that point, you're going to always intersect the sphere into 2 points. So you can always say that the interior point is the convex sum of those two points. So you could have multiple different probability distribution, but the von Neumann entropy is going to be corresponding to the one that it's the minimum. So this is sort of how the geometry of all of this works. Now, the part for discrete case in quantum mechanics is basically, well, straightforward in the sense that everything is well defined. Then, of course, you have to get an intuition for all these things. But it's certainly at least understandable and well defined. And now the problem is when you have countably infinite dimensional case. So the countably infinite dimensional case presents similar problem as the classical case and adds others. As in the classical infinite case, the maximally mixed state, that is a uniform distribution, is not in the convex space, and the entropy is not finite for all infinite convex combination. And in the classical continuous case, there is the issue of finite expectation of position and momentum in all frames. The problem is compounded by the fact that one cannot require finite expectation for all functions of position and momentum. So in classical mechanics, we said, if I have position and momentum and I require all the functions of position and momentum to have the finite expectation, you get distribution that have finite support in position and momentum. Good. You can't do that in quantum mechanics, because if you have finite support in position, automatically implies infinite support on momentum, since the distribution in momentum is the Fourier transform of that in position. So you can't have both the position and momentum bounded in the sense that the probability distribution is within a finite region. So this presents a problem. You can't just say, oh, I'm just going to look at at things that have finite support. Things have to go at infinity. Therefore, you have to characterize well how things go to infinity. And that's why, as I was saying before, infinity gets worse in quantum mechanics. You can't avoid it. You have to actually figure out how to treat it. Now, the Hilbert space for a discrete variable with infinite range, the number of particles, and a continuous variable position momentum is the same because they're both separable spaces. They're going to have countable bases, and Hilbert spaces that have the same number of bases, they are always isomorphic to each other. So the first is defined as the space of square converges complex sequence L square, while the second is the space of square interval function L capital square. And given that L square allows a countable basis, the two are isomorphic. This means that all spaces with finitely many degrees of freedom in quantum mechanics are also isomorphic. This makes the problem of infinite expectation even more problematic. Because if you say, I have 1 particles, I have 1 billion particles, the Hilbert space is the same. And so it's unclear to me that, well, it's clear to me that the Hilbert space is not the correct space. And it's unclear to me which is the correct one. And again, we can look at something just for inspiration. Note that the Schwartz space, note the Schwartz spaces have finite expectation for all polynomial functions of position and momentum. And the Schwartz space are the space of infinitely smooth functions that go to infinity faster than any polynomial. So for example, the Gaussian is something in the Schwartz space. It's infinitely smooth and it goes to infinity like an exponential. So the expectation of any polynomial is always finite. Given that infinite permutation can change the rate of convergence, as we saw before, the Schwartz space has an idea of what is farther away from the origin, unlike the Hilbert space. So that's probably a plus. And So we will likely want to use the Schwartz spaces instead of Hilbert spaces to make the physics and mathematics more consistent. So it's likely that when we are trying to recover quantum mechanics, we actually want to recover the Schwartz space and not the Hilbert space, because the Hilbert space is pathological, and we probably don't want to do it. We probably cannot recover it if we want to have physically meaningful starting assumptions. And it's just not going to work. So this is essentially all the review of the classical and the quantum case. And sort of that gives you an idea of all the problems that we have to go and look at when we are doing our theory. And the next section will start, developing the axiomatic and so on. I would leave this for next time at this point, because we are not going to be able to look at much, and I think this is a good stopping point anyway. So I can stop if there are questions, and if there are none, we can adjourn and figure out. I'll start looking at dates for when we want to have the next one while I see if there are questions. That would be 28. Yeah. Okay, so I would probably skip next week because it's right in between Christmas and New Year, and we can do the 4th. And again, because I'd rather that more people are live is to see if there are questions. So WWKK, was it clear? Were there any things that were like confusing, or I don't know, any take would be helpful, I guess. Ram says the parts I heard were clear enough. And this is the synthesis of things that I've been trying to pin down for the past year and a half. So hopefully they're digested. So okay, then we're just gonna stop. Is there anybody who has questions of any related topics? It would also be fine. Otherwise, we just stop. Hmm. I never know how long to wait because I never know what the delay is. Okay, the answer is in time for sure. Yeah, yeah. This is just the overview, and yeah. Okay, so we'll stop and Merry Christmas, Happy Holidays, and Happy New Year for everybody. And I'll see you. It's going to be the 4th, right? Yes. We're going to skip next Saturday. We're going to see everybody at the 4th. Bye, guys. Bye, everybody.